Have you ever wondered how we can be absolutely certain about every single part of a shape when we only have a few pieces of information? Well, today we're going to dive into a core concept in geometry that does exactly that, proving parts of triangles are congruent.
So, here's the game plan. First, we'll talk about this idea of corresponding parts. Then, I'm going to introduce you to a really powerful acronym that kind of works like a secret key. After that, we'll walk through a full proof to see it all in action. And we'll wrap things up with a special shortcut that only works for right triangles. Sound good? Let's jump in. All right, so first things first. Let's tackle a really important question. What happens right after you've done the work and proven that two triangles are congruent? What's next? I mean, think about it, right? We use these great shortcuts, side, 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 angle, or in this case, side, angle, side, to prove two triangles are basically identical twins. But if you look closely, we're only using 3 pieces of information from each triangle. So, what about the other 3 parts? And this, right here, is the crucial insight. The moment you use a shortcut to prove two triangles are congruent, boom, you've basically unlocked a treasure chest of information. Because the very definition of congruence means that all 6 corresponding parts match up perfectly. Every side, every angle, they're all congruent now. Okay, so how do we actually state this powerful conclusion in a formal proof? Well, there's a special tool for that, and it's an acronym that, trust me, you are going to see everywhere in geometry. And here it is, CPCTC. Yeah, it's a bit of a mouthful, but it says exactly what it means. Corresponding parts of congruent triangles are congruent. This becomes your go-to justification. It's the logical step you write down in a proof to say, hey, I already proved the triangles are congruent, so now I can claim that these specific matching parts are congruent too.
And this really hits the nail on the head. CPCTC isn't a method to prove the triangles are congruent. Think of it as the logical bridge you cross after you've already done that hard work. It's what allows you to make all these other claims about specific sides and angles.
All right, enough theory. Let's get our hands dirty and see this in action. We're going to walk through a formal 2-column proof, step by step, to see exactly where CPCTC comes into play. Okay, so here's our puzzle. We've got this diagram, and here's what we know. That line WZ cuts the top angle perfectly in half, and we also know that side WT and side WV are the same length. Our mission? To prove that the bottom segment is split perfectly in 2, that TZ is congruent to VZ. Every proof starts the same way. You just state what they gave you. So we know for a fact that WZ bisects angle TWV. Let's put that down as statement number 1. The reason is simple. It was given.
Now let's unpack that first clue. What does bisect an angle actually mean? Well, by definition, it just means it splits the angle into 2 smaller, perfectly equal angles. So our next logical step is to say that angle TWZ is congruent to angle VWZ.
All right, let's move on to our next given. We were also told that side WT is congruent to side WV. So let's get that down on the board as our third statement.
Now, this next part is a classic move in geometry proofs. You'll see this one all the time. Notice how both of our smaller triangles, TWZ and VWZ, share that middle side, WZ. Well, since a line is always congruent to itself, we can state that WZ is congruent to WZ. The official reason for this is the identity property, which you might also hear called the reflexive property. Okay, let's just step back for a second and see what we've collected. We have a side from step 3, an angle from step 2, and another side from step 4. Wait a second, they're in perfect side-angle-side order. That's it. That's exactly what we need. We can now officially state that triangle TWZ is congruent to triangle VWZ.
And here it is, the moment we've been building up to. We've proven the triangles are congruent. So what does that unlock? It means we can now look at their other corresponding parts. The side TZ on the left triangle must correspond to the side VZ on the right. Therefore, they have to be congruent. And our reason? The star of the show, CPCTC. And just like that, the proof is done.
But don't think the story ends there. The real power of CPCTC is that once you've done the heavy lifting of proving the triangles are congruent, you can draw all sorts of other conclusions from the very same diagram. For example, what if the problem had asked us to prove that the base angles were equal? Well, we would follow the exact same first 5 steps, but for our last step, step 6, we'd simply state that angle T is congruent to angle V, and again, we'd use CPCTC as our reason. Or we could even add another layer. We just proved that TZ is congruent to VZ. Well, if a line segment like WZ is dividing another segment, TV, into two equal parts, what does that make it? By definition, that's a segment bisector. So we could even add a seventh step to our proof and conclude that WZ bisects TV.
Now, let's shift gears and look at a very special case. There's a powerful shortcut for proving congruence that applies only, and I really mean only, to right triangles.
First, let's get our terms straight. In any right triangle, the ones with a 90-degree angle, the two sides that form that right angle are called the legs. And the side opposite the right angle, which is always the longest one, is called the hypotenuse.
This special terminology leads us to a really slick shortcut, the hypotenuse leg theorem, or just HL for short. It's a beautifully simple rule just for right triangles. If you can show that the hypotenuses are congruent and one pair of legs are congruent, then the triangles are congruent. That's it. You're done.
So whenever you see right triangles in a problem, you should run through this little mental checklist. First, do I actually have two right triangles? Check. Second, are the hypotenuses congruent? Check. And third, is at least one pair of corresponding legs congruent? If you can check all three of those boxes, you've proven congruence by HL.
So we've unlocked the power of CPCTC and the HL shortcut. But here's the biggest takeaway. Triangles are the secret building blocks of almost every other shape. By proving little triangles inside them are congruent, you can prove that the diagonals of a rectangle are equal, or that the opposite sides of a parallelogram are congruent. This stuff isn't just about triangles. It's the key to understanding a huge chunk of geometry. So the only question left is, what are you going to prove next?